Hi everyone, welcome. My name is Raoul Schaffranek, and this talk is about revolutionizing Solidity debugging with symbolic execution. So you may have heard of debugging, and you might have heard of symbolic execution, and this talk is really about the intersection of these techniques. So a little bit about me. I'm Raoul. I'm head of developer tooling at Runtime Verification. And I joined the company in 2021. Before that, I did some formal verification in the distributed system space and in Web 2. I also worked as an auditor, as a formal verification engineer at Runtime Verification. And this experience is basically what made me think of new tools. Like, what are the tools that I need to be more productive and be more confident about the security reviews that I did. So this is the agenda of today's talk. So I want to touch on 4 points. I want to touch on debugging, and then I want to touch on symbolic debugging, which is just an extension of classical debugging. I want to talk on testing and on symbolic testing, which is yet again an extension of classical testing techniques. And at Runtime Verification, we are developing 2 tools to support both of these activities. So we have Symbolic, which is a symbolic execution debugger, and we have Control, which is a symbolic testing framework. And the cool thing about these is that they are really tightly integrated tools. So you can use Control to write symbolic tests and prove your tests. And if something fails, you can use Symbolic, kind of a debugger, to debug your failing tests. And vice versa, Symbolic, everything that you do is Symbolic, is powered by Control under the hood. So that means at the end, when you're finished running a debugging session, at the end, you will find a counterexample that is the manifestation of a bug, or you will get a proof that no such bug can exist according to your specification. So there's this famous quote from Dijkstra: if debugging is the process of removing software bugs, then programming must be the process of putting them in. And I think, well, we can all agree with this quote. So, and yet, we have very good tools for writing code. We have good IDEs, we have syntax highlighting, we have auto-completion, we have GitHub Copilot to write code for us. So we have very good tools to put bugs into our code, yet we don't have so many tools for debugging. And the way I like to think of a debugger is basically, a debugger is a cool tool to find bugs in your code. I use it as a reading assistant. So because when you're doing code reviews, it's very hard to keep track of all the variables that are changed in the code. You need to keep track of the control flow, the data flow, and then there's a lot of context switching when you go from one file to another file to see what this function in this other file is doing when it's called from this function that's yet in another file. So you have these context switches, you have these you have to keep track of all the variables in your head. So basically, when you're reviewing code, then you're building a huge mental model, and you need to keep all this stuff in your mind, and then, well, an email notification pops up, and your mental model just vanishes. And everybody knows that feeling then. After the email notification, after you read that email, you go back to the code and you start like reviewing it from scratch. Like, there's not much of a process that you could save before. So, and with a debugger, you now have an assistant that can act like as an external mind, like an external memory. Like when you're reading code, you're actually executing it step by step in your debugger. And the debugger takes care of keeping track of all the variables, so you don't have to do it mentally. And it also makes it easier for you to do these context switches because, well, the debugger will jump into a function. When you hit it, it will open the source code for you. You can set breakpoints and stuff. So that means now when this email notification pops in, your debugger paused in some state, you read this email, you answer it, you come back, your debugger is still in this paused state. You can remind yourself real quick, okay, what was the contents of the variables? Where am I paused in my execution? What's my call stack? Like, all this stuff that you have to keep track of mentally can now be kept off. The debugger is now keeping track of this. And we're developing such a debugger for Solidity, and it's called Symbolic. And one way of thinking of Symbolic is it's a classical debugger. You can set breakpoints, you can step through the code, you can inspect the variables, you can even go down and inspect the bytecode level. You can execute over single instructions. So all the nice features that you would expect from a debugger are present in Symbolic. It's still in early development, so there's probably something that you miss or a feature that you would like to have. And if you do so, please just reach out and message us. What is the feature that you like to have the most? And then we can adjust our development process to support what you wish to have from a debugger. So it's available on the Visual Studio Code Marketplace. You can just install it. There's some additional instructions that you need to follow because you need to get a free API key from our website, but it's perfectly free to use. And the tool is like 90% open source. And the remaining components will be open sourced over the next weeks. It's just they are not stable enough yet. So then you all know what is debugging. So now what's symbolic debugging? And it's an extension of debugging, as I said before, where I think concrete debugging is a very cool tool, for example, to debug failing tests, or to build a mental model, like I just described, keeping track of all the variables and the control flow and stuff. Debug is also a good tool to showcase proof of concepts. Like if you've found a bug somewhere, you can actually show it and explain it to your teammates or to your clients or whoever authored the code base and walk them step by step over the proof of concept so that you can together collaboratively reproduce the counterexample. Now, symbolic debugging is an extension, and instead of just exploring a single execution path, it really explores all possible execution paths. And that's a very good tool to refine your understanding. Like when you use a classical debugger, you're mostly interested in some edge cases or maybe in the happy path, so you debug some execution paths. But once you have this mental model, you want to go deeper, you want to see all the edge cases. And that's where symbolic debug is really handy in refining your mental model and making it more precise. It's also a cool tool to discover proof of concepts because, well, it will explore all program paths. And it forces you to go over every single program path, every single edge case. And well, as an editor or a security researcher, that's actually what you want to do because it's sufficient for your protocol to get hacked if there's only a single execution path that is buggy, right? And then it's also a cool tool to discover new test cases as opposed to just debugging failing tests. Let's do a quick exercise on what symbolic execution is. I won't go into the mathematical details, but you are already you have a very good intuition of how symbolic execution works, because when you're reading code, you're actually reading it symbolically. So let's start with a simple example. So we have some initial state, and this initial state so we are looking at this. In this code snippet, this could be the part of a simple transfer function from an NFT or from a ERC20 token, for example. So when you're reading this code, you can make sense of it pretty quickly in your head. But I want to do it very slowly now, just to explain you some concepts of symbolic execution and introduce some vocabulary. So we start in an initial state. This initial state has some value, some from, and some to variable. Oh, there's a typo there. That should be to, not foo. And all these variables, these top three variables, we say we don't make any assumptions about them. They could be fully symbolic. They could be anything. And then we say, okay, the balance of the from address is 100. 100 is a concrete value as opposed to a symbolic value. So when you see something with $1 here, that means symbolic value. If you see a constant, like an integer, that's a concrete value. That's the difference between the two. Now we want to execute this if statement. And with the information that we have from our initial state, we cannot actually say if this if statement is going to visit the then branch or if it's going to visit the else branch. So what we do in symbolic execution, well, we just do both. We visit both program paths. So, and in the one state, like in the then branch, we've learned some additional knowledge because we now know that the condition must be satisfied. So we add this constraint, which is called a path condition, to a state that says, well, 100 is less than $value, then we're executing the revert statement and this branch is done, good. But we still have to look at the other branch because we want to look at all branches really. So in the other branch, we know that the opposite of this condition must be true or we wouldn't be in the else branch. So then we execute the next statement, which is just a state update. The state update here can also be symbolic. So the new value of the from address is now 100 minus $value. So it's a more complex symbolic value. It's just not a variable, but it's a constant minus some variable. And then we execute the next statement, which is not very interesting. So wouldn't it be very cool, like if we can visualize and draw these graphs automatically for all of your code? And that's what Symbolic can do. So if you look at this screenshot, you can see this is the code on the left-hand side that we are executing, and on the right-hand side, we are drawing the execution graph for you. So and this is really listing out all possible code paths that are reachable from your initial state. And there's no exceptions. This is really complete. So if you're a security reviewer or an auditor, that's very cool because think of you're doing a code review and you want to check all the edge cases, and now you have a tool that displays them to you, and you can just go there, click one of those nodes. The debugger will load the state directly into the debugger. You can see what's going on, and you can make a check mark on this program path. And if you've checkmarked all the program paths at the end, well, then you really went over all possible edge cases, no exceptions. And I really mean no exceptions. So at the end, what you get is really a proof that that none of your states, none of your reachable code paths can violate the properties that you were checking. Of course, this checking with the debugger is still a manual process. So you have to go, click on every single edge case, and inspect the states. But we will talk later about control, which is symbolic testing. And control is really automating out this last step of you manually checking the boxes on every possible edge case. Some theory. Ethereum is a state system, a state transition system. So you have states, which is mostly the storage of your accounts, the balances of all the accounts, and then you have transactions, which are just state transitions, and they update the global state somehow. They maybe update the storage of some contract, or they update the balance of some account. So state transition system, very basic. So now in the past, well, Ethereum has some initial state that was mined in 2015, and then from there we recorded a bunch of transactions, like thousands or millions, I don't know, and every single transaction triggered a state update. And we know that some of these state updates have been exploits, so there have been buggy states, and well, that's what we want to avoid, right? But now finding these exploits and understanding them is already very difficult. So, but now we are here in the presence, and the future in front of the problem in front of us is even bigger, because we want to avoid bugs, but we don't know how the state transition system will evolve. Like there are like billions of possible next transactions, and then after the next transaction, there's another billion options. So the state space is just so huge. And then, most of these transactions or most of these execution paths will probably be fine, but it's sufficient if there's just one bug in one transaction or in one state that can be exploited. So now we are like, how do we find this bug in a basically infinite state space? The way we do it with symbolic execution is, well, we collapse the state space into abstract states. So we start at the bottom in gray, there's concrete execution, and in yellow, at the top in gray, and at the bottom in yellow, there's symbolic execution. So in concrete execution, we start from some concrete initial state, maybe where Alice has 100 tokens and Bob has 0 tokens. And we're going to debug a transfer from function that sends tokens from Alice to Bob with an amount of 10, Alice to Bob, amount of 20, Alice to Alice, 30 tokens. And then, well, you can see that there's already almost an infinite amount of choices that you can make for the transfer function, right? And no matter what parameters you choose, you will end up in a different successor state. So this state space is huge, it's infinite. What we do in symbolic execution is instead, we say, we don't make so much assumptions about the initial state. We say, hey, the balance of the from address is X. The balance of the to address is Y. Then we execute the transfer from function on this abstract state. We leave it completely open. What is the from address, what is the to address, and what is the value address? And at the end, we will get just two successor states that are, again, abstract states. So, and one state represents the case where the from address and the receiving address are different. So one account gets credited, the other account gets debited. And then there's the case where somebody tries to send tokens to himself, so the balances all stay the same, ideally. So that makes it possible for us to represent like infinite many states in a finite representation. And the cool thing is now, I'm going to skip this slide because that's very technical. The cool thing is now that we reduced this giant problem of finding bugs in the future, like big state space, hard to find bugs, you don't know how many transactions you will need to trigger the bug. And we reduced that problem to a way simpler problem of finding a bug in an abstract transaction. And that's symbolic execution, basically. I have to say a word about symbolic. I talked about the symbolic execution mode. The symbolic execution mode is not shipped yet into the Visual Studio Code extension that you can download and run locally on your computer. But there's a demo that we have. So you can go to trysymbolic.runtimeverification.com and it will load a Visual Studio Code in your browser, and that allows you to symbolically execute and debug wrapped ETH. This mode is not so stable yet that it's not publicly available, but if you are like a security-minded company developing a protocol, please reach out. We can make this available to our clients earlier than the public release, which will probably take some more time to develop to iron out all the edge cases. Okay, now let's talk about testing. And since you are at a security event, I assume you all know what testing is. And you know probably what is unit testing, what is fuzz and property testing, but not so many people are using symbolic testing, which is a bummer because, well, we all like fuzzing, right? Because, well, it gives us more confidence in just unit testing. So in the same way, symbolic testing allows us to build a greater confidence in our test suite without actually modifying the code, without actually modifying the test suite. We can use the same Foundry test suite almost unmodified and throw it into control and test it symbolically, and it gives us very strong correctness properties. So this is the saying, or this is this quote, again from Dijkstra, says, program testing can be used to show the presence of bugs, but never to show their absence. And that's really true, and nobody would dispute it. But I would say that symbolic testing or formal verification in general is the closest that you can get to show the absence of bugs. There's some philosophical issue here, what constitutes a bug? And formal verification does not solve this problem. But what we do in formal verification and symbolic testing as well, you have a specification, a formal specification, and everything that does not conform to your specification, that's a bug. But then, is your specification complete? That's another problem, right? And in some ways, it's a way harder problem. So let's make this more concrete. So how does a fuzzer work? You have a smart contract as an input, and you have a test suite, a specification, and then at the end, the fuzzer maybe gives you a counterexample, which means, hey, it found a bug. That's great. Now you can go fix the code. Or it says, well, your test case passed. But this passed is actually what is not so cool, because what it's actually saying is, I'm not sure. I haven't tried all the inputs, but for the inputs I tried, I haven't found this counterexample. But maybe there's another one. Maybe I should just keep fuzzing for 24 more hours, for another week, for another month to find this bug. But obviously, well, you will never get to the state where the fuzzer fully explored all possible states, because your state space is just so huge. So if we want to get full input coverage over all parameter combinations, we need to be more clever than testing all the possible inputs one at a time. And that's again where symbolic testing comes in. So symbolic testing has the same inputs. It takes a smart contract, a test specification, and then instead of a fuzzer, you have a prover in the middle, and it can give you 3 outputs. The first one is a counterexample. You found a bug, great, fix your code. The second one is, I'm not sure, I'm kind of stuck here. And that's kind of similar to, so this red state here is similar to what a fuzzer says when it said test passed. But we can also give you this proof of correctness that says, we fully explored your entire state space. We went into every single edge case, and we can 100% guarantee you that none of the test cases is breakable. The tool that we use to do symbolic execution at runtime verification or symbolic testing is called control, and it's basically the combination of 2 techniques that we are developing. We are developing a formal semantics of EVM, which is called KVM, and I think this is alive since 2016, so it's the longest standing formal semantics of the Ethereum, of the EVM. I think it's also the most complete, most precise, and most maintained formal specification. And then we have, on the other hand, we have Foundry, which showed to be very useful in finding bugs with fuzzing and property testing. So, and what control is, it's the marriage of these two tools. It's marrying Foundry to the KVM, and now you can use your Foundry specifications, feed them into control, and control will try to prove that your tests pass, or it will find a counterexample, or will get stuck. So control is not so hard to use. It's a command line tool. The comments are very similar, intentionally very similar to Foundry. So instead of Foundry build, you do control build. Instead of Foundry test, you do control proof. And then there's some additional features, functionalities that you can use to debug the states where your prover gets stuck. So that's a unique capability of control is also, well, proving and formal verification in general can never be a push-button solution where you press a button and it says green or red, but there's always the case where it gets somewhere stuck, and then you need to, well, make progress on the proof, and control is one of the formal verification tools that can actually always make progress towards your end goal. So you're never fully stuck and lost, but you're stuck, but there's a clear path forward, and there's tools that you can use to make progress. Some more cool features about control and symbolic. Control is fully open source. Symbolic at the moment, 90% open source, will be fully open sourced soon. Control can reason about loops, which many formal verification tools can't. I think there's only Daphne EVM that can reason about loops. And yeah, I think it's only Daphne EVM and control basically that can confidentially reason about loops. And you would say, okay, my Solidity smart contract doesn't have loops, so why should I be interested? And I can guarantee your smart contract has loops, even if they are not on the Solidity level, they are existent on the bytecode level, because the Solidity compiler will generate bytecode level loops in all kinds of scenarios. Control is also, it does not make any simplifying assumptions about the execution layer. It's everything that is in the Ethereum yellow paper is 100% modeled accurately and precise in control. All the states, when you get stuck, most provers just say proof passed, I found a counterexample, or I got stuck, and when you're stuck, you're lost. Control lets you inspect what's going on. It lets you inspect the stuck state so that you can make progress. And well, there's this benchmark suite that's comparing different formal verification tools available for EVM and Solidity. There's this repository called ETH-SC-Comp Benchmarks, where we're trying to compare these different tools. And Control is the best in class in terms of solved instances. So even though it's a semi-automated tool, it's able to find the most proofs fully automatically. Yeah, some selfish, selfless, some shameless self-advertisement. So there's also this nice formal verification panel happening later today. Please join us. We have great panelists from other formal verification companies or companies who are using formal verification to develop their products. And yeah, that's it for me. These are the links to our social media channels. This is my Twitter. Oh, this slide is kind of messed up. But yeah, you will find it. And if you have any questions on Control on Symbolic, fetch me after the talk or join some of our social media channels. If our tools are not what you expect them to be, if you're missing a feature in the debugger or in the control, just let us know and we can probably make it happen. If we get a feature request often enough, we are more likely to make it happen. All right, thank you.
Thank you.